In this video we're going to examine the formation of mid-level cloud, that is altocumulus, altostratus or ACAS. So altostratus is stratiform cloud and altocumulus is convective cloud, and very often you see the two together, stratiform cloud in the mid-levels of the atmosphere with embedded convective elements. We'll consider four mechanisms: what's known as warm air advection, the advection of moisture, lifting, and finally upper level divergence. So consider a cloud band in the atmosphere, so a large region of ACAS. We can apply a simple warm air advection model to explain its existence. Consider wind that blows from warm air to cooler air. That's known as warm air advection because parcels of air are moved from their original location into a cooler environment. Consider too that the flow is isentropic. That is, parcels of air don't exchange heat with their environment, so theta is constant, and they're isentropes because entropy is also constant. If you take Poisson's equation for potential temperature and differentiate it and assume d theta is 0, the definition of an isentrope, and rearrange the equation, you get the equation shown there that changes in temperature dt are related to changes in pressure dp. And so if we have warm air advection and parcels are moving from warm to cool, it must mean that their pressure is decreasing over time. That is, they're ascending. And so isentropes typically slope from warm air to cool air. So if the flow is adiabatic, warm air advection implies that air is rising and cloud bands are going to form. So if we look at this infrared satellite image, you'll see a couple of cold fronts and some cloud bands associated with those. So that's the large regions of sheet-like looking cloud. There's one associated with the front that's passed through Perth and another one associated with the front that's in the Tasman Sea. So let's look at some model output. Here now what we have is the height, what's known as the geopotential height of the 700 hectopascal surface. And the orange line indicates the demarcation between what we're calling a warm air and cool air, and then the blue line indicates the region of cold air. Also marked the temperature lines in blue. So here now is the same picture at the same time for 500 hectopascals. So it's the height of the 500 hectopascal surface, and the heights as it changes as you move north and south are shown in the brown, and the temperature lines are shown in the blue, but also shaded, so that the red is the coolest values and the blue is the warmest values. You can see that there is a feature off Western Australia that's associated with very cold values. Now what's shown here is a region where we can infer from these values of geopotential that the wind is northwesterly to northerly, and the winds are blowing from the blue shades, which are the warm values, to the green shades and yellow shades, which are the cool values. And so we have warm air advection in that region. And if you go back to the satellite image, you can see that that's associated with a large area of cloud. So this is our cloud band formed by warm air advection or upslide. The blue oval there is a location of a sonde, and here we have the sonde profile for Eucla. Are there any hints that you can see in this environment that suggest warm air advection? Stop the video and have a think. So what did you come up with? Well, we can see that the winds are northwesterly, and so typically because conditions are warmer further to the north than they are further south, we can infer that there's warm air advection. And as will be examined in dynamics, the winds backing with height, that is winds that turn in a counterclockwise sense, will tell us that there's warm air advection. But you can see that there's been an increase in temperature in the last 12 hours. So the blue trace is 12 hours ago, and you can see that the red trace is further to the right compared to that. And so there's been warming at that location, which infers, or from which you can infer warm air advection. There's also warming just below the cloud base, which is indicative of a change in air masses between the two levels. So there's warm air advection happening above that, and so you've got that weak adversion as well. So that's all indicative of warm air advection and producing cloud as a result. So let's look at some examples of how that might look in an area forecast. Remember, an area forecast is a forecast over an area for a period of 12 hours or so, and is meant to broadly describe the broad scale pattern. So here we have, for example, a forecast that says ACAS above 12,000 feet. Or one could write ACAS 12,000 feet, which is the base, to 25,000 feet, which is the top. Now, of course, on an area forecast, your region of responsibility finishes at 18,500 feet. So either form is correct. It's always useful to have determining qualifiers as well. So, for example, in north of the area, which might sound vague, but at least it tells you that the cloud band doesn't exist for the entire of the area, or a temporal determining qualifier, so contracting to east to become west of a line, and then you can put in things like time. A real example is shown in the last line. It says areas of broken ACAS above 10,000 feet in northeast, so it contains all the information we want. It's areas, so it's not broken everywhere. It's broken, so there's more than half the sky. It's ACAS, and it's above 10,000 feet, and it's in the northeast of the area. As a final note, we don't normally mention mid-level cloud on TAFs, but sometimes you may want to do so, particularly if you're forecasting rain, which is associated with mid-level cloud bands.